let's show that the transformation t, which flips the x1 and x2 coordinates, is linear, and let's see exactly how that looks when we try applying it to a couple different vectors. Now note, even though I didn't say it, t has domain and codomain R2. So remember, to show that t is linear, consider generic vectors u1, u2, v1, v2 in R2, right, the domain, and maybe some generic real number. So we have first that t of u1 plus v1, u2 plus v2, right, that's just these two vectors added together. That's going to equal, well, let's just flip them, right? u2 plus v2, u1 plus v1. And note that that's the same thing as u2, u1 plus v2, v1. And that's the same thing as t of u, let me just put that on the bottom here. T of u, u1, u2 plus t of v1, v2. Right? And just in case that's not crystal clear, this is the same thing as t of u1, u2 plus v1, v2. Okay? So t of u1, u2 plus v1, v2 equals t of u1, u2 plus t of u1, v2. All right? So that's good. Now for the second property, t of c times the vector u1, u2, or in other words, t of, you can just start with this if you prefer, cu1, cu2 is going to equal cu2, cu1. So what I did there, just flipped the coordinates right there. Okay? And maybe you can see that that's the same as c times the vector u2, u1. And maybe you can see that that's the same as c times t of u1, u2. So sure enough, both of them check out. So t is a linear transformation. Now, let's see what it does, right? We're going to consider the vectors 5, 2, and negative 2, 4, right? So if we just get a couple axes going. What we're going to do is we'll just consider a generic vector 5, 2. Maybe that's this guy. And what happens? Well, we're sending it to the vector 2, 5. So if you think about it, it's that. And then what about the vector negative 2, 4? Maybe I'll use black for that. Negative 2, 4. So that looks something like this. That's going to get flipped to 4, negative 2. So it's like here, so. So what you might want to notice is that each of these vectors is getting flipped over the line x1 equals x2. Right? Compare the oranges, right? That's where it's getting mapped. Compare the black vectors, right? That's, right? That's where it got mapped. So if in general we consider some big space, I'll use a highlighter for this, like maybe I'll just use the red highlighter for example. If we consider where does, say, this space go, well, it's going to be flipped, right? Imagine taking that and like ripping it off like it's a sticker or something. And so it's going to be over here. Oh. Okay, so just to give you an idea, that's what that linear transformation looks like, okay? Really quickly, just in general, the transformation T is linear if and only if we can extend this to arbitrarily many vectors. If T of, let's say, C1 V1 plus C2 V2, etc., plus Cn Vn equals C1 T of V1 plus blah, 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 plus Cn T of Vn. Okay? That's equivalent to the definition we stated before, right? No, it's the same thing, it's just, it's more than two vectors and more than two scalars, right? You can prove that if you really want to prove it, you can use induction. Anyway, quick little example, right? Suppose we've got these vectors, they span Rn, we've got a linear transformation, but T of each of those vectors equals 0. Show that T is actually the 0 transformation. So what we do is we say, okay, well, consider these vectors, I'll just say V1 through VP, and any or every C1 through CP in R, right? Any scalars that you want. So T of, I'll keep that up there, C1 V1 plus blah, 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 plus CP VP equals, again, by the definition of linearity, C1 T of V1 plus blah, 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 plus CP T of VP, right? We can split over scalar multiplication and addition. But we know by assumption that that's C1 times 0 plus C2 times 0 plus blah, blah, blah plus CP times 0. I should say the 0 vector, that is. And that, of course, equals 0. Okay, so you have it.